Hello, everybody. Welcome to Chapter 11 of the Biology 141 class. This is a chapter that is talking about how muscles produce movements. Most of the details will come to us in lab. When you look at this set of lecture slides, you'll see that we cut out most of the Chapter 11 material from a textbook. This will be a short chapter for us, and therefore on lecture exam 4, there will be only a small handful of questions from chapter 11. Again, most of the muscle growth anatomy and how they produce movement will come to us in the lab. You'll see the wonderful details that we cover in those 3 muscle labs. So let me go into screen sharing and let's take a look at these lecture slides. What do we want to say about how muscles produce movement? So here is the first look at chapter 11. We will be talking about voluntarily controlled organs, skeletal muscles. 700 plus skeletal muscles make up the muscular system. This is where we start to angle a little bit more organically towards the nervous system. You'll see the role of nervous system several times in this chapter, especially when it comes to muscle coordination. We will continue that in chapter 12, and then we'll continue also in chapter 14, where we mention some of the brain structures involved in controlling the muscular system. In terms of the connection to the nervous system, in chapter 10, we already had a lecture where we talked about the neuromuscular junction with all the wonderful processes, the release of the neurotransmitters from inside the neuron, the opening of the sodium channels on the muscle cells, and the excitation contraction coupling. So that was our first event where we were introduced into the role of the nervous system. Here we're going to see further evidence. No surprise, all skeletal muscles are controlled by our nervous system. So let's take a look. Very, very basic aspects. It seems like kindergarten stuff, but when it comes to designing skeletal muscles to create movements, the designer has to keep in mind the skeletal muscles can only shorten, they contract. They always pull on the bones, sometimes on skin. They never push. So we'll be seeing very soon concrete examples of that. So this is one aspect to consider. The other aspect, very basic aspect of how muscles produce movement is that muscles need to grab onto 2 particular structures. One structure is the origin. The origin is usually a bony or a strong tendinous structure that does not move when the muscle is contracting. The insertion, the other end of the muscle, is the movable end, and it is moving most likely bone, sometimes muscle. And so origin insertion, really important for considering muscle activity. So I'm going to point here at the biceps brachii muscle. This will come up in our second muscle lab. The origin of the biceps brachii is on the scapula. The origin is not detailed in tremendous detail. The insertion of the biceps brachii is on the radial tuberosity of the radius. And so this muscle is going to produce movement by creating a force, relying on a solid support of the scapula in moving the radial tuberosity, which will eventually result in a move of the forearm. Biceps brachii is a muscle that flexes the forearm. Another basic aspect of muscles is that most skeletal muscles participate in a physical arrangement called lever system. So the lever system has three parts to it. Let's take a look at biceps brachii. We have the effort portion. This is the skeletal muscle where the contraction and force creation occurs. We do have a load. This is what the muscle is trying to move. And then we have a pivoting point, a turning point. It's usually some kind of a joint. This is called a fulcrum. So these three elements make up a lever system. We are not going to get into the physics of it whatsoever. It is important to know that skeletal muscles do participate in lever system. Just for informational purpose, here are three types of levers that we find in the body. We have a first-class lever. Most of the time, the first-class lever is providing a mechanical advantage. This muscle creates a tremendous force with these kind of first-class lever arrangement. The second-class lever arrangement, this would be exemplified when we stand on our toes, we carry our plantar flexion. If you imagine that the fulcrum is the ball of the joint of the big toe, the load is the entire body weight, and effort is this muscle. We'll cover this in the third lab, such as the gastrocnemius located in the calf area of the leg. It's going to move the entire load superiorly. This is second-class lever. This is yet again provides a mechanical advantage. Large forces can be created to move large loads, such as the entire body. The third-class levers sometimes produce a mechanical disadvantage. We're not gaining a force advantage from the biceps brachii muscle. Here, the advantage through the leverage system shows up as a advantage of the range of the motion that can be created here. Our forearm can be moved in almost 180-degree range. Excuse me. So this is the biological advantage most third-class levers give to skeletal muscle. So we are gaining some kind of an advantage. Depending on the need and the location, we either gain a mechanical and force advantage. A relatively little force can move a lot of load, a big load, or we gain a range advantage where relatively little force can produce a large range of movement. So I think I've said enough about levers. Again, don't spend a whole lot of time on this. It is important to know that skeletal muscles participate in lever systems. Another way to optimize the working of skeletal muscles, not only by their origin, insertion, and whether they participate in the first, second, or third-class lever, but fascicular arrangement. Fascicular arrangement can add muscle cells towards the middle of this muscle, and so the fusiform muscle will be thicker in cross-section than the parallel arrangement, and more muscle cells will create more force. So in the same physical location, we can jam-pack more muscle cells to create a fusiform type of muscle. This is seen in the biceps brachii. A parallel muscle arrangement typically will be looking at muscles around the neck. Maybe the sternocleidomastoid is not a bad example of that. In case when we need to close an orifice, we have a circular arrangement of the fascicles, these bundles of muscle cells. When these muscle cells contract, the orifice here is the eye is going to be closed. So this is orbicularis oculi muscle that closes the eye. We have a very similar muscle arrangement around the mouth. Take a look at the triangular arrangement, and this is the last one we're going to mention here. We pack a huge number of muscle cells into this muscle, yet all that force will be directed to this tendon towards the insertion. Our pectoralis major muscle is a typical example of that large area of origin. Many, many muscle cells create huge force to move the humerus, and we'll cover this in the second lab of the skeletal muscles. So these are all about optimizing the force or the range produced by skeletal muscles. And then comes the effect of the nervous system. Coordination makes skeletal muscle work very, very efficient. We try to avoid the action of opposing muscles when a movement is desired. So the desired movement is created by the prime mover or agonist muscle. Here again, let's use the example of biceps brachii. If you want to flex the forearm, the biceps brachii is the prime mover. Now we do have antagonist muscles, muscles that could extend the forearm, work against the biceps brachii, but thanks to the working of our nervous system, antagonist muscles made to relax, to yield to the prime mover. We'll be seeing this in a few minutes. And actually, here right now. So let's take a look at the two opposing muscles. Here, let me go to this end here. Here's biceps brachii, flexes the forearm. So when the biceps brachii is a prime mover, the forearm will be flexed. And right here, this muscle, the triceps brachii, will be made to relax. So how can we make a muscle to relax? We are not going to send any nerve impulses. The triceps and the biceps brachii have their neuromuscular junction. When we are flexing our forearm, neurons are sending nerve impulses through those neuromuscular junctions of the biceps brachii. But at the same time, our brain prevents sending nerve impulses to the triceps brachii. So the triceps remains relaxed and it just stretches along with the flexing of the forearm with the work of the prime mover. So this kind of coordination, again, comes about as the effect of our nervous system. Again, a number of brain structures are involved in creating not only the signal that goes to the biceps brachii, but also shutting down the signal that would go to the triceps brachii. The synergist muscles go into contraction together with the prime mover. So here are the fingers, right? The digit. The flexor digitorum muscle causes this grabbing-like movement, flexing of the fingers. When that happens, and if we especially hold onto very tight onto something, like if you're grabbing a steering wheel real tight, at the same time, the nerve impulses will also send automatically to this muscle extensor carpi, and that stabilizes the wrist. It makes the wrist immovable, so whatever we are holding onto so tight, we'll have very little chance to escape, and so we have a firm grip on whatever we are holding onto. How does our brain know that when we flex our fingers and holding tightly onto something to activate the extensor carpi muscle? Again, our nervous system carries out this coordination. When we flex our fingers, automatically nerve impulses will be sent to the synergist muscle, in this case, the extensor carpi muscle. In the lab, we'll be talking about several examples of fixators. Whenever an arm movement is created, and here the deltoid muscle will be abducting the arm, that abducting movement would depress the scapula, we would be moving it inferiorly. And to prevent that from happening, and we'll see in the lab in great detail just why we have to stabilize, fix the scapula in one place. So when the movement of the arm would displace the scapula inferiorly, move it downward, we have muscles that will be activated to elevate the scapula. You see on this side, and the scapula is totally covered by it, but you can see that the trapezius in part inserts on the scapular spine. And this insertion allows the trapezius to elevate the scapula when the deltoid would be, or the activity, contraction of deltoid would be pushing the scapula downward. There are other muscles that get activated, in this case, subclavius, we don't cover this in the lab. Serratus anterior also will be part of lab material. So whenever we abduct our arm, again, automatically nerve impulses are sent to the fixator muscles that will fix the scapula in place, prevent its motion. Again, we'll see a little better in the lab just why and where do we have to fix the scapula in one place. Again, coordination by our nervous system takes care of the fixating action. And what we have on the next few slides is a tour of muscles that we only partially or not cover whatsoever in the lab. So we look at several muscles of facial expression, like orbicularis oculi, orbicularis oris. We are not going to cover this muscle in the lab, levator palpebrae superioris. So orbicularis oculi, this muscle right here, this circular muscle, closes the eye. But to open the eye, we need to actually lift, elevate the upper eyelid. So the upper eyelid palpebrae superioris will be elevated by the levator muscle. And it's right here. This muscle carries out the elevation of the eyelid in a more deep section. You see it on the other side too. With the muscles of facial expression, here again, the role of the nervous system. All muscles of facial expression get their nerve impulses through this cranial nerve 7 or facial nerve. If this facial nerve is injured, there is a one-sided paralysis of the muscles that create the facial expression, and that create a drooping looking skin on that side of the face. There is a blog post that I wrote about Justin Bieber, who had this Bell's palsy, and his cranial nerve 7 was disabled on one side. This can be a major sign of stroke. A stroke may disable the brain portions or the origin of cranial nerve 7 and can lead to a paralysis of skeletal muscles, highly visible on the face. And that's a good sign to go and seek medical help. In AMP2, we'll be looking at muscles that move the eyeball. Here in AMP1, we're just going to punt on this topic. But when we look in our eye socket, we find 6 skeletal muscles, strap-like, thin skeletal muscles. The beginning, the origin is mostly on this tendinous ring at the posterior aspect of the eye socket. The insertion is always the sclera. The tendon of these muscles fuse with the sclera, and this is how these muscles can tug the sclera up or down, and together with that, of course, entire eye. We have 4 rectus muscles and 2 oblique muscles that move the eye. Cranial nerves 3, 4, and 6 bring nerve impulses to these muscles. Cranial nerves will come up big time in chapter 14. So it's not a bad idea to get familiar with the numbers. In the bone labs, you already mentioned cranial nerves, so 1, 2, and 8. Muscles that move the tongue will never come up in this detail, so let's talk about this. When you look at the muscle, when you look at the tongue itself, it's pure skeletal muscle. There's no bone in there. It's really challenging to move the tongue. And the movement of the tongue is achieved by assembling a range and a number of skeletal muscles with different origins and different movement ranges. So a few examples here. The genioglossus muscle originates from the symphysis of the mandible. We mentioned this in the lab. The fusion of the mandible creates this bony bump here. That is the origin of the genioglossus. Genioglossus, of course, ends up as being part of the tongue. Styloglossus originates from the styloid process, and you can see styloid process of the temporal bone here. Palatoglossus, this is probably the weirdest of the muscles of the tongue, originates from hard palate. Take a look here. From the superior aspect of the oral cavity, this muscle curves around on the side of the oral cavity and inserts into the tongue from below. So this is palatoglossus. And we have one hyoglossus originating from the hyoid bone. So these muscles with very different origins can create the movement of the tongue. When we speak, we need very specific movements of the tongue, but we also need the tongue to move during swallowing, really important for the proper working of our digestive system. In AMP2, we'll have a short exposure to voice production. Never going to go into this detail. So muscles move the vocal cord, they stretch it or move it laterally. And so take a look at this huge variety of the tiny skeletal muscles inside our larynx. So when you look at this large gray structure, this is our thyroid cartilage. Right here is the Adam's apple. So inside our larynx, there is this treasure trove of small muscles allowing us to create sound by moving, stretching, or relaxing our vocal cord. We didn't say much about detailed muscle attachment site in the lab, but this is a great view of some of the lumbar vertebrae here and one thoracic vertebra up here. When you look at the transverse processes, there are muscles connected, skeletal muscles connecting each transverse process. We do have muscle connecting the transverse process of lumbar 1 to the spinous process of thoracic 12. So vertebrae can be moved around each other. We also have this multifidus muscle that traverses the space between 3 vertebrae. So there is a large number of tiny skeletal muscles allowing sophisticated movement of the vertebrae, and this plays a great role in maintaining posture. When we faint, even from a sitting position, these skeletal muscles no longer receive nerve impulses, they relax, and then we lose our sitting position, we keel over. Before that, we will cover one muscle in the lab that is a major muscle used in breathing, inhalation, and exhalation. In AMP2, we'll go a little bit greater detail. So we have muscles between the ribs, external intercostals activate during inhalation. Our poster chart here in this semester for muscles of breathing will be the diaphragm. And let's take a look at the diaphragm from inferior position. You can see the origin of the diaphragm, Ziphod process, ribs of cartilage. This is really nice exposure. The unusual aspect of the diaphragm is that the insertion, the movable end, is inside this ball-shaped muscle, the central tendon. Another weird aspect of the diaphragm muscle that it has to have opening for things like the aorta, lymphatic vessels, the inferior vena cava, and the esophagus. So this muscle is like a bowl that has a number of holes in it, and all function in one way or another. And our last set of muscles are muscles of the pelvic floor. We never come, at least in AMP 102, never come back to these muscles. It is important to realize that the inferior aspect of our pelvic cavity, the pelvic outlet, needs to be covered up somehow. Otherwise, all our pelvic organs will be falling out through here. You can see the ischial tuberosities here. So how do we prevent all those organs from falling through that opening? Well, we create a layer of muscles and layers of connective tissue. This is called the pelvic floor or pelvic diaphragm. The biggest muscles that you see here, the coccygeus muscle, which is right here, and the levator ani, this muscle right here. Those are the two muscles that close up most of the space. Whether it's a female or male pelvic floor, both sexes need these muscles in a slightly different arrangement. Failure of these pelvic floor muscles lead to fecal or urinary incontinence. Failure of these muscles can also lead to the disorder called prolapse, where either the vagina, sometimes even the uterus, and both in males and females, the rectum would be protruding, coming out through these openings. So the proper strength of these muscles required, number one, for quality of life, and proper control of urination and defecation. So I'm going to stop sharing here. So this is it for chapter 11. Again, please ignore the huge volume of muscle origin, insertion, and action information in chapter 11. What we need from that, we will cover it in the lab for lecture, and therefore lecture exam 4 will leave most of chapter 11 out. So please focus on the lecture slides when you prepare for lecture exam 4, and you'll be fine. Most questions on lecture exam 4 will be coming from chapters 10, the muscular tissue, and chapter 12, nervous tissue. Lots of physiology will be challenging the exam. Don't study too much from chapter 11. Again, stick to the lecture slides, and you'll be fine answering those small handful of questions. So I'm going to close this lecture and send it your way in a few minutes. If you have any questions when you watch this, please don't hesitate to send me a message.